Welcome back. I'm going to move on to chapter 8.3, which is the second law, efficiency. Yeah, look at this. This efficiency has got this parallel line here, representing 2. Slightly different from the efficiency that we have done before. So the second law efficiency will be thermal efficiency divided by reversible, useful divided by reversible. Okay, for work consuming devices, producing is useful over reversible. Consuming will be the reciprocal of the other one. And for refrigerators and heat pump, COP divided by reversible. So what do you see? The similarity here. Everything is divided by perfect process. Yeah. Okay. Now let's consider this diagram here. Okay. Consider two heat engines, both having thermal efficiency of 30, and one heat engine A is supplied by heat source of 600 and the other by 1000. So this is 600, this is 1000. Okay, so both heat rejects the medium of 300 and 300. Yeah, at first glance both engines seems to convert work the same fraction of heat that they receive, but then they are performing equally well. When we take a look at the engines in light of the second law of thermodynamics, however, we see that the totally different picture. Yeah, so these engines, they at best can perform as reversible engines, which the efficiency could be 50 and 70. Okay, 50 and 70. Okay, so from there okay, this formula would be to get the reversible A. Reversible A is 1 minus TL over TH. Yeah, and this one would be 1 minus TL over TH. This is the reversible formula. You remember you have done this before. Yeah, it looks like something like this, equals to 1 minus TL over TH. Okay, so from there you can get this value of 50 and 70. Okay, you can just do it by yourself. Okay, now it is becoming apparent that engine B has greater work potential because it's 70%, right? Okay, and of heat supplied as compared to 50% of A, thus should do a lot better than A. Correct or not? Yeah, B looks like it's performing even better than A. Therefore, we can say engine B is performing poorly relative to engine A, even though both have the same thermal efficiency. Yeah, okay, they have same thermal efficiency. Okay, now it is obvious from this example that the first law efficiency alone is not enough. Yeah, not realistic enough to measure the performance of the engineering device. So to overcome this, that's the reason why we have the second law of efficiency. Okay, now if you put in this formula into the second law of efficiency, which is NTH, yeah, this one. Okay, so it means you put this 30 over 50, 30 over 70 into this formula, you get this calculation here. I've done this calculation here for you. Okay, what do you get? A as 0.6 and B as 0.43. That is, engine A is converting 60% of the available work potential to useful work. And the ratio for B is only 0.43. So what does it say? The second law of efficiency can also be expressed as a ratio of useful work divided by the maximum possible of work output. So we see here that A is even better than B. Yeah, so that is why we have to study this second law of efficiency. So now let's move on to the example. Okay, let's look at an example. Yeah, a dealer advertises that he has received shipment of electrical resistance heater for residential building that have efficiency of 100%. Wow, so perfect. Huh? Assuming an indoor temperature is 21 and the outdoor is 10, determine the second law of efficiency. Okay, so this is a heater. So we use COP, yeah, coefficient of performance of heat pump. For reversible will be 1 over 1 minus TLTH. So what do you get? 26.7. That is, it should supply the house with 26.7 units of heat extracted from the cold outside air for each unit of electrical that's consumed. From the second law of efficiency, because COP is actually 1. So where do you get the COP1? That is from the supplier, which actually said 100%, can deliver 100%. Yeah. So the usefulness is actually 1 divided by 26, which is only 3.7. So the dealer will not be happy to see this value. Consider the high price of electricity. A consumer will probably be better off with less efficient gas heater. So this is the reason why we use this calculation. So discussion 5, the second law of efficiency of this electrical heater can also be determined directly from equation where 1 minus T naught over TH, which is also 3.7. Okay. What is the conclusion of this 3.7? What does it mean? What does it mean? What meaning it carries? Yeah. Okay. It means that 96.3% of the heat can never be converted to electrical energy. So that is the meaning. Yeah. Therefore, we can change our mind and decide to convert the heat back to electricity. The best we can do is actually 3.7. So only 3.7 can be converted back, whereas the other 96.3 is irreversible. Okay, so that is the meaning of the interpretation of this formula and also the question. I hope you understand this. Okay, thank you. So that is the end for this chapter 8, chapter X-City. The other part of 8.4 onwards is not coming out in your syllabus, so you don't have to look at it. Yeah, so we stop at 8.3. Thank you.